Okay, to follow up on our conversation last time about tree maps, we can talk about specific type of tree. There's something called a binary search tree, and there are certain rules that are applied to the specific type of tree, BST, in order for it to be called a BST. So on the left side, the subtree has to be smaller than a node. And then on the right side, it has to be bigger than the node. So let's look at this tree. If we just, oops, chaos. Okay, so if we have this tree here, there we go. If we have this tree here, let's look at the depth 0 and depth 1, so the first and second layer. To the left of 2 must be smaller, but in this case it's not. It's a 3. So this disqualifies this tree as BST. So it doesn't really matter whatever else falls below. But we could fix this if, let's say, we took the 3 out, right? And we just have the 1. So we have 2, 1, 5, 3, 7, 4, 6, 8. This would be an unbalanced tree, but that's another thing. 1 is smaller than 2, so that's fine. And because there are no other children or other elements, then we can look on the right subtree. To the right we have 5. So 5 in relationship to 2 is bigger. So that works out. And then 7 to the right of 5 is bigger, so that checks out. And then 8 is bigger than 7, so that checks out. All right, now looking at the subtree. So if we're getting the root, let's look at the subtree, which starts at 5. Now 5 becomes a reference point. 5 is a node here. To the left of the node is 3, and it has to be smaller, so yeah, that's fine. To the right, we already talked about this. 7 is bigger than 5, so that checks out. 8 is bigger than 7, that checks out. Now look at these smaller subtrees of that subtree. 3 to the left has nothing, so we don't have to worry about it. To the right we have 4. Well, 4 is bigger than 3, so that's fine. Looking at this subtree with 7 as a new reference point. The node is 7. 6 to the left of 7 is smaller, so that works out. And we already talked about how 8 is bigger than 7. Good deal. So now let's zoom out and see the big tree again. The minimum value is always the most left element, so that's 1. And the maximum value is always the most right element, so 8. And so we can say the height is 1, 2, 3, 4 minus 1 is 3. Actually, I think it's 4. Oops. The reason being, there are 4 layers, but when you call those layers, you start counting from 0. So it's depth or height, whatever you call it. Depth is 0, 1, 2, 3. But there are 4 layers, so the height is 4. I believe it's that. Otherwise, it's 3. I need to check on that. But here's a great example of a BST without needing to correct it. Okay, reset the board. Instead of numbers, I used the office because the office is great. Using Oscar as the node, or like the root parent. I'm just using a bunch of synonyms here. Using Oscar as a node. To the left of Oscar is Jim, and J is smaller than O. To the left of Jim, using Jim as a reference, is Creed. Okay, Creed is smaller than J because C comes before J. That checks out. Looking at the right side, R comes after O, so it's bigger than O, that works. T comes after R, so that works out. Now look at the subtrees individually. Jim has 2 minions under him, Creed and Kevin. We already know that Creed checks out. What about Kevin? Kevin's to the right of Jim, so K has to come after J, which it does, so that's fine. And then Ryan, we already know Toby is situated well. What about Pam? Pam is to the left of Ryan. P comes before R. So that checks out. The minimum value being Creed, maximum value being Toby. So if you put all these humans' names in a alphabetical order, Creed is the first name in that list, and then Toby is the last name, like the very last name in that list. So maximum value is Toby. Programmatically, this is how you can create a tree. You can use a tuple and then wrap it in parentheses, and then it'll know, okay, here's how I'll draw it. But right now the tree is kind of not rotated, so you just have to flip it 90 degrees clockwise. Yeah. And I did it with the numbers as well as the alphabets, because alphabets can be sorted as well. So yeah, let's talk about a balanced versus unbalanced tree. This is a balanced tree because from Oscar, when we split to the left and right, his departments are evenly split out. So maybe this is a sales team, maybe this is like back office. I don't know. You can call it whatever. It's a mix because you've got you've got HR, you got front desk, and you got an intern. So we'll just call them like extras or something. Oh yeah, and these are finance and compliance. Okay, whatever. So forget about that. Let's say they're in a special project and they're split out like this. It's pretty balanced because you've got a team of three, and they all answer to Oscar. Here we have where we chose Creed to be the top leader, which is kind of scary. I'm thinking of that episode where Pam asked him to compare the two images and find the differences. But they were exactly the same. So yeah, so he's in charge. And there's no one, Angela is not in the office today, so then there's no one to split out on the left because J comes after C and then KF comes after J. So when you create this tree, making Creed the boss, then the structure becomes unbalanced and it's just one person answering the other. So it's really inefficient. And in this case, you can actually see all the cast members alphabetically organized. Creed, Jim, Kevin, Oscar, Pam, Ryan, Toby. So yeah, anyways, that's a difference between balanced and unbalanced tree. And then here's how you can program and say, hey, instead of me telling you, like in a tuple, how the elements should be placed, I'm just going to say, here are the rules. Left subtrees must be smaller, right subtrees must be bigger. And whatever that subtree follows, whether it's a subtree of the subtree or the subtree of the subtree of the subtree, whatever that is, that reference is called a node. And then just looking at the node, to the left is smaller, to the right is bigger. So apply that rule and boom, draw my tree. So it knows, all right, here's your tree. And I asked for it to also tell me the height. So how it looks is it looks on the left side and the right side, and it counts. Okay, depth 0, 1, 2, layer 1, 2, 3. Because it counts as 0, you just have to add a 1 at the end. So, okay, that confirms earlier what I was saying about how there are 4 layers. Yeah. Anyways, so the height is 3 because there are 3 tiers. And then it drew out the tree perfectly. It matches like the manual way. And then I also drew the unbalanced tree, so it knew to choose the very first guy in the alphabetized list. So I knew Creed was the first, and then instead of going upwards, it should go downwards because this tree has to be rotated 90 degrees. Anyways, let me see. Like this. There you go. This is what the tree looks like. Yeah. So, this is just another way where I called, instead of filling in like a list of names. I just asked it to call on a database I created earlier. So anyways, yeah. What's cool is it stores their information. So it's not just the element and the key being their name. It also has values. Oh, if you pull up Creed, here's his username, his full name, Creed Bratton, and his email, creedbratton@dundermifflin.com. So yeah, this is just a more complete and fancier code. And again, looking at the unbalanced tree, because we said to use a rule, instead of writing out the tuple saying Creed, comma, Jim, comma, da da da, and wrapping in parentheses, we just said with a tree C, the parent node or the very first node is going to be none, and then for username, user in our data, which calls on my stored list of the office cast, and then insert the tree with username and user. So there you go. That's what it looks like. Yeah.